From excavators built for sub-zero oil sands to draglines moving overburden across 300 feet in a single pass, mining machinery is defined by engineering trade-offs. At this scale, power alone isn't enough. Uptime, efficiency, and reliability determine whether a mine stays profitable. If you value real output and real engineering trade-offs, subscribe for future breakdowns on production machinery. Quarry operators running extended shifts face a direct trade-off between fuel costs and throughput. The Volvo EC950F addresses this with a system that reduces consumption without proportionally reducing output. ECO mode optimizes the hydraulic system and 603 horsepower engine to reduce fuel consumption by up to 25% under specific load conditions, while maintaining the 8 cubic yard buckets cycle time. The system adapts based on material density and operator input, rather than simply limiting power. Safety features include oversized platforms, reinforced handrails, anti-slip surfaces, and cab visibility designed for close-quarters operations. Norwegian quarries report these machines maintain 18-hour shifts in sub-zero temperatures, though uptime depends heavily on maintenance intervals and material hardness. Fuel efficiency matters, but when mines operate at extreme altitudes where thin air affects engine performance, durability becomes the primary concern. Mines at altitude present a specific challenge where reduced air density cuts engine performance, while abrasive materials accelerate wear on components. The Liebherr R996B is designed for extended service intervals in these environments. The 36 cubic meter bucket uses wear-resistant steel alloys, and the hydraulic system operates at high pressures while remaining balanced enough to provide operators tactile feedback on dig resistance. The cab includes fire suppression and automatic lubrication systems that extend service intervals. In Chilean copper mines at 15,000 feet altitude, the high-powered hydraulics compensate for reduced air density. Operators report 80,000-plus operating hours before major overhauls, though this varies by material type and maintenance protocols. Performance at altitude depends on proper tuning for local conditions. Altitude and durability solve certain problems, but active mining zones with heavy traffic create a different challenge entirely, one where visibility becomes critical to safety. Large excavators create blind spots that increase collision risk in active mining zones. Komatsu PC7000-11 integrates camera and sensor systems directly into the operational workflow. The ComVision system provides 360-degree visibility around the excavator using multiple cameras, displaying real-time feeds inside the cab. This allows operators to track approaching vehicles, personnel, and obstacles during the 38 cubic meter shovel's swing cycle. The Tier 4 final engine reduces emissions by up to 80% compared to older models while maintaining power output. The payload meter measures load weight per scoop, helping operators load trucks to target capacity and reduce wasted cycles. Indonesian coal mines report productivity increases of approximately 40% after deployment, though results depend on operator training and site logistics. Visibility and emissions control address operational safety and regulation, but some materials demand machines built specifically for their unique properties. Oil sands present a specific excavation challenge. The material is sticky, abrasive, and becomes significantly harder in winter temperatures. The Demag H740OS was designed specifically for Canadian oil sands operations, where conventional excavators struggle with both the material properties and extreme cold. At 744 tons, this machine uses a diesel-electric hybrid powertrain. The 4,000 horsepower engine generates electricity that powers hydraulic pumps with computer-controlled precision, producing a 2,320 kilopascals breakout force. The hybrid system uses approximately 35% less fuel than conventional excavators of similar size, though actual savings depend on material conditions and cycle times. The 40 cubic meter bucket is engineered with heating elements that prevent oil sand from freezing to the steel in temperatures reaching -40 degrees Fahrenheit. The hybrid system also enables regenerative braking during swing operations, recovering energy and feeding it back into the system. Canadian operations report this machine works 20-hour shifts in conditions that sideline conventional excavators within weeks, with durability coming from components tested to withstand 1 million load cycles. Purpose-built designs solve material-specific problems, but when operations scale up, the time spent repositioning the excavator itself becomes a significant cost factor. Moving the excavator itself consumes time and fuel, which becomes significant in large-scale mining operations. The Hitachi EX8000-7 addresses this with extended reach that reduces repositioning frequency. The machine can dig 73 feet horizontally and 27 feet deep without moving its tracks. That 52 cubic meter bucket under optimal conditions can move enough material to fill an Olympic swimming pool every hour, though actual output depends on material density and haul truck coordination. The modular arrangement means maintenance happens on wide platforms accessible from ground level. The centralized lubrication system allows one person to service the entire machine in approximately 45 minutes, compared to 4 hours on comparable excavators. The 1,944 horsepower engine powers hydraulic pumps operating at pressures exceeding 5,000 psi, generating breakout forces capable of fracturing bedrock. Australian iron ore mines have measured 99.7% uptime over 12-month periods with the EX8007, though this requires strict adherence to maintenance schedules. Extended reach reduces repositioning time, but another approach to maintaining productivity involves redundancy in the power system itself. We focus on how machines actually perform in real operations. Subscribe if that's what you're here for. At 768 tons with 2 engines producing 4,020 combined horsepower, the PC8011 takes an unusual approach to power distribution. The dual-engine configuration serves 2 purposes: redundancy and optimized power delivery. If one engine needs service, the excavator can still operate at reduced capacity, eliminating total shutdown downtime. When both 3,000 kilowatt engines run together, they generate torquey curves that deliver maximum force across every RPM range. The 42 cubic meter bucket moves with notable speed for a machine this massive. The dual engine setup powers independent hydraulic circuits, one optimized for boom and stick, another for bucket and swing. This separation eliminates power lag during complex operations. Chilean copper mines use these to move approximately 12,000 tons of material per shift per machine, though output varies with material hardness and haul distances. Advanced safety systems include pitch and roll sensors that prevent operation on unsafe slopes. The reinforced structure has demonstrated it can run 100,000 plus hours in abrasive conditions, provided maintenance intervals are followed. Dual engines provide redundancy and power distribution, but there's another way to address operating costs at scale through energy recovery systems. At 881.9 tons, the Liebherr R98000 represents decades of refinement in excavator design. Fuel consumption at this scale becomes a significant operating cost. Liebherr's energy recovery system captures hydraulic energy during boom lowering and swing deceleration, storing it in accumulators and feeding it back during the next power cycle. This regenerative system can save approximately 120,000 liters of fuel annually under typical operating conditions, though actual savings depend on cycle patterns and material type. The 57.5 cubic yard bucket delivers an 84-ton lift capacity. The 4,023 horsepower engine maintains optimal power across all operations, while the fuel-saving technology adapts to material density in real time. The cab offers visibility designed to minimize blind spots, and lifetime upgradable components mean excavators from 2015 can receive technology retrofits. Mines report 80,000 plus operating hours before major component replacement, equivalent to nearly a decade of continuous operation under proper maintenance. Energy recovery addresses fuel costs at the 881-ton scale, but the engineering challenges multiply further when pushing into truly extreme sizes. The Caterpillar 6090FS is the largest hydraulic excavator currently in production. At 1,102.3 tons, the engineering challenge becomes managing hydraulic forces at unprecedented scale. 8 main hydraulic pumps, each flowing 936 liters per minute, are synchronized by computers operating 1,000 times per second. The 4,500 horsepower engine generates enough electricity to power a small town. A 103-ton bucket payload in a single scoop requires hydraulic systems operating at 5,220 pounds per square inch travel pressure and 5,080 pounds per square inch swing pressure, forces sufficient to crush structural steel. The cab stands 7 feet tall inside and includes climate control, air suspension seating, and display screens showing real-time data from over 300 sensors throughout the machine. Emergency escape systems include secondary ladders and rapid egress hatches. The swing system uses counterweights and hydraulic dampeners to eliminate oscillation, allowing this 1,000-ton machine to stop moving instantly when commanded. Energy optimization during acceleration reduces fuel consumption despite the massive size. Chilean and Australian mining operations report this single excavator can do the work of 3 smaller machines while using approximately 50% more fuel total. Though efficiency depends on material conditions and operator technique. The machine holds approximately 3,450 gallons of hydraulic oil total, with a 2,640-gallon tank capacity, powering cylinders with bore diameters exceeding 16 inches and stroke lengths over 12 feet. Hydraulic excavators reached their current size limit with the 6090 FS, but draglines approached material removal from a fundamentally different angle, trading mobility for reach. Only 2 Bucyrus-Erie 3270W draglines were ever built, both operated by AMAX coal. This exclusivity came from the machine's size and the specific operational requirements they addressed. Both machines used 176 cubic yard buckets on 330-foot booms, a reach extreme enough to dig the length of a football field without repositioning. At 17.5 million pounds each, moving these machines required careful planning and significant downtime. The Lot 1 machine operated at a Max's Delta mine in Marion, Illinois, while Lot 2 worked the Ayrshire mine near Chandler, Indiana. Built nearly simultaneously, they represented 1970s dragline engineering at its peak. The 176-yard bucket could handle approximately 130 tons of overburden in one drag, and the 330-foot boom meant these machines stripped massive areas with minimal walking. The dual machine strategy allowed AMAX to optimize maintenance schedules. When one went down for service, the other maintained production. The 3,270 watts represented extreme reach in dragline design, but one machine pushed every dimension even further. At 27 million pounds, Big Muskie was the largest walking dragline ever built. From 1969 to 1991, it operated at the Muskingum mine in eastern Ohio, moving overburden to access high-sulfur coal seams. The machine consumed 14,000 to 18,000 kilowatts per hour, generating up to 52,500 horsepower continuously. The dimensions defined its operational constraints. At 240 feet tall, 150 feet wide, and 487 feet long, the machine required extraordinary planning just to assemble. The 220 cubic yard bucket could lift 325 tons at once. A Caterpillar D9 bulldozer could fit inside the bucket with room to spare. It took 300 rail cars and 250 trucks to transport Big Muskie's parts to the site in 1967, and assembly required 2 full years. Once operational, the walking dragline ran 24 hours daily, stopping only for 30-minute crew meal breaks, repairs, and Christmas Day. 4 7-person crews rotated continuously, stripping away soil and rock layers covering the coal seams. The operation was economically viable as long as high-sulfur coal remained marketable. The 1990 Clean Air Act changed the economics. New regulations favored low-sulfur coal and natural gas, making high-sulfur coal operations unviable. Big Muskie was retired in 1991. Despite preservation efforts, it was dismantled in 1999 because the cost to maintain and relocate the machine exceeded available funding. The land Big Muskie once mined has been restored as part of the Wilds, one of North America's largest wildlife conservation centers. Where the dragline once operated, giraffes, rhinos, and cheetahs now roam across 10,000 reclaimed acres. These machines demonstrate the engineering trade-offs required when operating at extreme scale. Power versus efficiency, reach versus mobility, output versus fuel consumption. Each was designed to solve specific operational constraints in large-scale mining. If you're interested in how production machinery actually performs under real conditions, subscribe for future analysis. We cover the engineering decisions, operational realities, and measurable trade-offs that define industrial equipment.